Hello students, welcome back. In this lecture, we're going to discuss ways to describe data, displaying and exploring. This is going to be chapter 4 in our statistics textbook. Let's start. So the learning objectives of this lecture are going to be construct and interpret a dot plot, identify and compute measures of position, construct and analyze a box plot, compute and interpret the coefficient of skewness, create and interpret a scatter diagram, compute and interpret the correlation coefficient, and develop and explain a contingency table. So let's start with the first one, which is the dot plots. So we can use the dot plots to compare the two data sets like these. So we have the Tionesta Fort Lincoln, which is going to be the number of vehicles serviced in the last month, and then we're going to have the number of vehicles serviced last month in the Sheffield Motors Inc. And so dot plots are going to be useful for comparing two different data sets, and so we're going to have a particular plot for the Tionesta Fort Lincoln, and we're also going to have a particular plot for Sheffield Motors Inc. Okay, and so we will use dot plots to show the difference in location and dispersion of the observations. So in order to develop a dot plot, we will display a dot for each observation along the horizontal number line, and if there are identical values, the dots are piled up on top of each other. Okay, so let's take a look of an example of dot plot. Here we have an example of dot plot using Minitab, and we can observe dot plot for both the Tionesta and the Sheffield. Okay, and so as you can see, the distribution of the observations between the Tionesta and the Sheffield is quite different. As you can see, the distribution of the Sheffield is relatively to the right of the distribution of the Tionesta, and this is evident from the mean. So the sample mean of the Sheffield is going to be 35.83, and the sample mean for the Tionesta is going to be 31.92. So you can see that the distribution of the Sheffield is to the right and of the Tionesta, and it has larger values of the mean. Okay. Another thing that we can observe is that the number of vehicles serviced at the Sheffield dealership is more widely dispersed than the Tionesta dealership. Okay. Now it's also important to note that the identities of the individual values have not been lost in these dot plots. So this is another interesting feature of the dot plots that we can have. So another ways of describing the data is actually through measures of position. So we'll start by a measure of location that describe the shape of the distribution, and one of them is percentile. So the location of a percentile is the following: L of P is equal to n plus 1 P divided by 100. Okay. So percentile, we're going to divide it into 100. So you have the first percentile, the second percentile, third percentile, fourth percentile, 5th percentile, until the 99th percentile, and so on, and the 100th percentile. Okay. Now, in addition to percentile, we also have quartiles. So quartile is going to divide a set of observations into 4 equal parts. Now, if we have the quartiles, we can actually calculate what's called the interquartile range. So the interquartile range is going to be the difference between the third quartile and the first quartile. Recall, interquartile range is going to be different with range, where range is going to be the difference between the maximum and the minimum values. The interquartile range is the difference between the third and the first quartile. We have a percentile, we have a quartile, we can also have a decile. So a decile divides a set of observations into 10 equal parts. Okay, so you have the first decile, the second decile, the third decile, the fourth decile, and so on. And so for many applications, it's useful for us not only to know the mean or the median, we also would like to know the distribution of percentiles. I think that's also quite important. Okay. So another thing that is going to be useful is the way that we use this decile or quartile or percentile. So for example, 25% of the data is going to be less than the first quartile, 50% of the data is less than the second quartile, and 75% of the data is going to be less than the third quartile. Now the interquartile range, which is the difference between the third and the first quartile, is actually going to cover the middle 50% of the data. Very useful statistics to have given a data set. Now let's discuss an example of using measures of position. So Morgan Stanley is an investment company with offices located throughout the United States. Listed below are the commissions earned last month by a sample of 15 brokers. So you have commission of 2038 until a commission of 1460. First thing that you're going to do before you calculate percentile, quartile, decile is to sort the data from the smallest to the largest. Okay, and so in this particular case, the smallest observation happens to be $1,460, and the largest observation happens to be 2,406. Now, the next thing that we want to do is we're going to calculate several interesting positions. So the first one is going to be the median. So the median is actually similar to the 50th percentile. Okay, and so in this particular case, the median is going to be 15 plus 1 multiplied by 50 divided by 100. And so in this particular case, the percentile or the median is going to be equal to 8. And so let's find out the 8th observation after we arrange the data set from the smallest to the largest. And so the 8th position happens to be 2038. So the median of the data is going to be 2038. Now what about the 25th percentile, and what about the 75th percentile? So again, the 25th percentile is similar to the first quartile. The 75th percentile is similar to the third quartile. Okay, and so the 25th percentile or the first quartile is going to be equal to the 4th position, and the 75th or the third quartile is going to be the 12th position. So if you look at the data that is ordered from the smallest to the largest, the 4th position is going to be 1721, and the third quartile or the 12th position is going to be 2205. Okay, so this is going to be examples of the measures of position. Now, a box plot is a graphic that displays the general shape of a variable's distribution. It is based on 5 descriptive statistics: the maximum, the minimum values, the first and the third quartiles, and the median. And so given that you have the first and the third quartile, you'll be able to calculate the interquartile range. Given the minimum and the maximum, you'll be able to get the range. So in a box plot, you can get the range. In a box plot, you can get an interquartile range, and in a box plot, you can actually identify the median. Okay, so outliers are values that are inconsistent with the rest of the data, and it's going to be identified with asterisk in box plots. Okay, oops, my apology. So what we're going to do is we're going to begin by drawing a number line that will accommodate the minimum and the maximum values, and then we're going to draw a vertical line above the median, the Q1 and Q3. Okay, and so we're going to enclose the regions between the first and the third quartile, and then the enclosed regions is going to create the box. Okay, now the next thing, we're going to draw dotted line segments from the third quartile to the maximum value and from the first quartile to the smallest value. Okay, so this shows the largest 25% and the smallest 25% respectively. So if you take a look at the distance between the third quartile and the maximum value, it's going to show you the largest 25%. And if you take a look at the distance between Q1 and the minimum value, it's going to provide you with the smallest 25% of the data. Now, as discussed previously, the interquartile range, which is the difference between the third quartile and the first quartile, is the middle 50% of the data. Okay, let's do a box plot on this particular example. So Alexander's Pizza offers a free delivery of its pizza within 15 miles. How long does a typical delivery take? So within what range will most deliveries be completed? So suppose that you have a random sample of 20 deliveries. Alexander determined the following. So you have the minimum value of 13 minutes. And so the smallest value in your box plot will be 13. The highest value in your box plot will be 30 minutes. Excuse me. And then you have the first quartile of 15, the third quartile of 22, and then you have the median of 18. So you're going to have an enclosed region between 15 and 22 with a median of 18. Okay, so now let's look at the box plot. So we're going to start by drawing a number line. Again, we have the minimum and we have the maximum. And then we're going to draw a box that begins at the first quartile, 15 minutes, and ends at the third quartile of 22 minutes. And we're going to draw a vertical line right at the median, and the median in this particular case is going to be 18 minutes. Okay, so we're going to extend a horizontal line from the Q3 to the maximum, and a horizontal line from the Q1 to the minimum value. And so we have the following box plot. Okay, so what can we say about the shape of the distribution? Now, if you look at the box plot, then the box plot reveals that the data is positively skewed. Why? Because the dashed line to the right of the box, which is between 22 to 30 minutes, is actually longer than the dashed line to the left of the box, which is between 15 minutes to 13 minutes. Okay? And another thing to notice why the distribution is skewed is that the median is not located in the center of the box. The median is located relatively to the left of the box, and so this indicates that the data is skewed, and in particular, it is positively skewed. Okay, so now, given that we touched upon positively skewed distribution, it's always good to know or to recall the common shapes of data. Again, not all of the data that you're going to observe are going to be symmetric, where the mean, the median, and the mode is going to be similar. In reality, we're going to have skewed distribution. And so, for example, we have a positively skewed distribution. We gave an example before that an example of positively skewed distribution includes income or household expenditures. And in a positively skewed distribution, the mean is going to be larger than the median. We also talked about a negatively skewed distribution in the previous lecture, and an example of a negatively skewed distribution is going to be test scores. So in this particular case, median is going to be higher than the mean, Again, because of the mean is dragged by the small number of observations with relatively low values. Okay. Now, another thing that you may observe is a bimodal distribution. So a bimodal shape has two, or it could have more than two peaks, and this may indicate two or more population have been combined. Okay, and so suppose that you combine two populations. So for example, you combined female population and the male population, and then from the male and the female population you're going to draw a distribution of the height or the distribution of the weight for the sake of example, and you may see a bimodal distribution. Okay. Now, given that we touched upon skewed distribution, it's good to know how skewed is a distribution. Now, to identify how skewed a distribution is, we can use the skewness or the coefficient of skewness. So the coefficient of skewness is a measure of the symmetry of a distribution. And so Professor Carl Pearson developed the simplest formula for calculating skewness, which is based on the difference between the mean and the median. And so since it is developed by Professor Carl Pearson, then we name it as the Pearson's coefficient of skewness, which is 3 times the difference between the sample mean and the median divided by the standard deviation. Okay. You can also use software coefficient of skewness, however, it's a relatively more complex calculation. Okay. Now, what are the values of coefficient of skewness? Well, the values of the coefficient can range from -3 to +3. So if you have a value near -3, it's going to indicate a considerably negative skewness. If you have a value of 163, it's going to indicate a moderate positive skewness. If you have a value of 3, it's going to be an indicator of a considerably positive skewness. And if you have a coefficient skewness of 0, it means that distribution is symmetrical. Now let's take an example of skewness. So the following are the earnings per share for a sample of 15 software companies for the year 2018. The earnings per share are arranged from the smallest to the largest. Now, let's find the mean, the median, and the standard deviation and find the coefficient of skewness. Now, given the coefficient of skewness, what can you conclude about the shape of the distribution? Okay, now let's first calculate the mean, the median, and then the skewness using the Pearson's formula. So the mean is going to be the ratio between the sum of the values of the sample divided by the number of sample, and in this particular case is $4.95. And the standard deviation is going to be the square root of the sum of the square difference between the value and the sample mean divided by n minus 1. So in this particular case, you have $5.22. Now, let's compute the skewness, and the skewness is 3 times the difference between the sample mean and the median divided by standard deviation. And so we have a coefficient of skewness of 1.017, and so what we can conclude is that we have a positively skewed distribution, and looking by the value of the skewness, we have moderately positive skewness. Okay, so far we've looked at data for just one particular variable. However, in many applications, you're going to look at the relationship of 2 variables, or perhaps in later discussions, we're going to look at the relationship between more than 2 variables. So suppose that we have two variables, and then what we're going to do is we can have a scatter diagram. So a scatter diagram is going to be a graphical technique to show the relationship between two variables, and we need two variables with interval or ratio scales. Okay. Now, if the scatter of points move to the lower left to the upper right, so we're going to have a positively related variables. If the scatter of points move from the upper left to the lower right, then the variables are negatively related, or they have a negative relationship. Okay. Now, just as a terminology, if you study the relationship between two variables in the data, then it's going to be referred to as bivariate. Okay. If you study just one variable in the data, it's going to be called univariate analysis. Okay, so let's take a look at different examples of scatter diagrams. So if we have a variable that moves from the bottom left to the upper right, so we have a positively correlated variable. If you move from the top left to the bottom right, you're going to have a negative relationship between the two variables. Okay. Now, one thing that we haven't discussed is actually the second graph, which is the graph in the middle. Okay, so the middle graph displays no relationship between the batting average and home runs. So home runs is the number of bats that is pushed beyond the perimeter of the ballpark. Batting average is the number of batting that you can get from a particular outing. So this is a particular statistics that we have in the baseball. Okay, so again, the middle graph displays that there is no relationship between the batting average and the home run. So those with a higher batting average doesn't necessarily have higher number of home runs. Another interesting statistic that we can calculate is called the correlation coefficient. So correlation coefficient is the measure of the direction and strength of the relationship between two variables. So suppose that we have two variables in our bivariate analysis, and the two variables are x and y. So the correlation coefficient is going to be the sum of x minus x bar, y minus y bar divided by n minus 1 multiplied by the standard deviation of x and the standard deviation of y. So the correlation coefficient can range to from minus 1 to plus 1. So the closer the coefficient is to -1 or 1, it's going to provide you with an indication that the relationship is relatively strong. If r is close to 0, then we can claim that there is no relationship between y and x, or for any two variables that we're interested in. Okay, so we have two examples of variables y and x. One that has a negative correlation and the other one has a positive correlation. So the one on the left with the perfect negative correlation, we have a correlation coefficient of -1, and for the right we have a correlation coefficient of +1. Okay. So far in the analysis of scatter diagrams, correlation coefficient, we looked at two variables with at least interval level of measurement. So we can also accommodate analysis of variables with nominal scale or categorical variable. And in this particular example, we can use contingency tables. So a contingency table is used to classify nominal scale or categorical variable according to two characteristics. So for example, we have the number of students by age group and by gender. So you have gender on the rows and you have age group on the columns, for example. So it's usually referred to as the cross tabulation that summarizes the two variables. Okay. Now the variables that we can use are nominal or categorical variable or ordinal variable, so variable with ranking. Well, can you use interval or ratio level data at all? The answer is yes. However, you need to convert the interval or the ratio variable into a nominal or ordinal. I'll provide you an example. So I mentioned earlier that we can actually make a cross tabulation or a contingency table of the number of students by age group and gender. So age group is actually derived from an age variable. So suppose that you have students ranging from age 22 until 30, then you can make an age group of 22 until 25, 26 until 28, and then 29, 30. So you have 3 age groups. Okay. Now in that case, you can convert age, which is a ratio variable, into a ordinal variable, or actually a categorical variable of age groups. Okay. So let's take a look at Applewood's auto group's profit comparison. Okay. So again, profit is actually going to be a ratio variable. Now what you can do is you can convert the profit into a ordinal variable. In this case is above and below. So we can also have a contingency table or a cross tabulation between above and below median profit by the dealership. Okay. So given that it's the median, then we're going to have 90 cars sold above the profit, above the median, has a profit above the median, and then 90 of the 180 cars sold will have a profit below. Will have a profit below the median. Okay, and so what's interesting is that we can observe the percentage of profits above the median in Kane, Olean, Sheffield, and Tionesta. So we can observe that in Kane there are 48% of profits above the median. In Olean there are 50% of profit above the median. You can calculate this by 20 divided by 40 multiplied by 100%. In Sheffield you have 42% of profits above the median, and in Tionesta you have 60% of the profit above the median. Okay, so so cross tabulation or a contingency table is going to group categorical. In this case is the Kane, Olean, Sheffield, and Tionesta, and categorical variable of above or below the median profit. And the above and below median profit is actually derived or converted from a ratio and interval. So thank you so much for your attention. This is going to be the end of chapter 4, and thank you.